VHDL projects where we practice creating different interesting systems in VHDL to help sharpen your skills in the language. And in today's video, we will be designing a right shift register. And a shift register shifts the content of the register left or right by 1 bit in each clock cycle. One major application of a shift register is to send parallel data through a serial line. In the transmitting end, a data word is first loaded to the register in parallel and is then shifted out 1 bit at a time. In the receiving end, the data word is shifted 1 bit at a time and reassembled. So this can be very useful in systems such as communication systems where we have a lot of transmitters and receivers. So in our simple shifter register today, we will be shifting in 1, shifting it to the right, and the data here is going to be inputted from our input here, D. So we're going to have the D is going to be constant, and in each clock cycle we are going to shift it inside, and the output Q will output the least significant bit of this particular output of the register. So what we expect to have is that our output Q will be 0 until we are at the 4th clock cycle, where we will have 1. As usual, the best practice is to divide our system into 3 parts, where we have our output logic, we have our D flip-flop logic, and we have our next state logic. So I will then now go through the process of creating this project in Visual Studio. And to do that, if you have not watched the previous videos where I explain the process of creating a new project in Visual Studio and running our project in using Python, then you should go back and watch our first video. So to do this, you create new, you go to open file, and then go to where you're storing your projects. In my case, I'm storing them here, and create a new file just to keep things neat. You have, so we are having our right shift register. Actually, let's just have it so then we open. We should have open folder, and then you should have open folder, and then you go to here, then you create your folder the same way by right clicking and creating new. After that, you open it, you select the folder, and we're in. So I'm just going to maximize this for now as we go through the process. So we are going to have one VHDL file where we'll have our right shift register dot VHDL. Then we also have our test bench, which is going to be right shift register dot VHDL. And to compile and run our program in Python, we're going to have run.py like that. So as I said before, you can copy this Python file and just be using it to run your projects by simply changing here. For instance, you have your right shift register, and don't forget to make sure that this is .vhdl. We've run into some problems by this. And then you also need to compile your test bench, which is now going to be test bench right shift register, and make sure this is VHDL. So the beauty of this is that if you're going to have a lot of projects to compile in bigger projects, you're going to have a lot of files here. You're going to have a lot of different components and so many of them here. So instead of you compiling them one by one, you can simply write all of them here like this, and then you run this run.python, and it compiles everything and is able to run your program. It's also very efficient in that once it compiles anything, that if you try to rerun again, and if you rerun again, it doesn't compile your project once again if the project are not modified. And it's also quite fast compared to Model Sim or things in terms of running small projects. So once you have this file, you can pause the video and simply copy this. There are some few things you need to install. Just look at our introductory video and you'll be able to understand. So now that we have this down, I'm going now to go to the processor. I'm going now to write the programs for our Redshift register, and I will just first of all write the entire code. You can write with me. However, I will finish it and then I will explain what I've done. So as I said, now I've completed writing the code. So just to explain, so we start with importing our libraries, and then we have our ports. And you may have noticed that I've changed the name. It's always good practice to completely name your circuits, or to completely use full names, such that it will be easier for you to debug your code later on. So having completed this, we have our inputs and outputs. We have our clock, our reset, D as input here, and then we have Q as our output. So then we have signals, which are these signals here that we can see from the D flip-flop and to the D flip-flop. And then, as usual, we first of all need to divide our circuit into three parts, where we have our D flip-flop logic, we also have our output logic, our next state logic, and we have our output logic. So if we say that now, we can just concentrate on one section. We start with our D flip-flop logic, and since our reset is asynchronous, we don't really wait for the clock. If reset is 1, then our output, which is our register, output of the register, is going to be 0. And this is how you write, you make sure that all the bits are 0. And then we have rising edge of the clock, where after each clock now we make our next state to be our current state. And then now we go to our next state logic, where we take our input, our input here, and we shift out the least significant bit, where we take this signal here. We will take the first 3 and concatenate it with D, and for our output we simply take the least significant bit of our signal here. So that's it for this particular Redshift register. Now we're going to write the test bench, and for us to write the test bench, I will write the code for the test bench, and then I will explain. So for our test bench, what I simply did is we defined our test bench, and okay, first of all, this libraries here that we imported from for VUnit is so that we'll be able to use VUnit in order to run our VHDL code, to compile and run our VHDL code. So you must have this, you must copy and paste these libraries, and then you also must use this test runner also here, and then you must use this just when you open your process. You must also have this first, and at the end you must also have this, and so your test bench comes in the middle. So what we did is using the component that we've just developed, we call the component here, and then we set our reset to 1 and waited for a few 2 clock cycles. In fact, here we should now set our reset to 0. Set our reset to 0 so that our program can run, and then we initialized D, which is our input, and then we waited for 5 clock cycles. So what we're expecting to see is that actually our signal our register signal, let me just go to what we're expecting to see is that this R register signal, we will see it start from 00, 1000, 1100, like that, and then finally we're going to see that our output Q now will be 1 after approximately about 4 clock cycles. So now and here we simply instantiated our component, and we used the port map here. So now let's compile and run our project, and to do that we simply go to new terminal, and then we say run.py, and instantly we see we have an error. So we must use Python. We must use Python run.py. I'm a bit tired today, so it's going to take some few minutes because my computer is running a lot of other things. Otherwise, it's usually very quick. So now we are compiling. So it says that in our test that there's an error in our test bench, line number 14. We seems to have a missing line number 14. Yes, this is an assignment. It's not supposed to be like that. Compilation failed. So seems to have a problem, big problem in our test bench. Line number 30. So it says there's no declaration for reset. No declaration for reset. We did not declare this as our signals. Before we do that, we are supposed to declare our signals, and to easily do that, we can do this. This is why Visual Studio is very good. You can easily do things very quickly. So you can have 1, 2, 3, 4. So you can have to use this select, by the way, simply push. For you to select like this, just push the middle, your scroll on your mouse. Just push the scroll on your mouse, and you'll be able to use this effect to select your signal like this and write multiple lines at the same time. Okay, so oops. So it seems like now compilation has passed. So now to view our simulation, we say run GUI, and here we have it. So let's see, these are our inputs. Let's see. Okay, there is a problem because we can see that our clock is not going anywhere. What is the reason for this? This is because we did not initialize our clock. We must initialize our clock in order for it to actually work. So let's compile once again. Compilation passed, and let's run it once again. Okay, so we also want to observe, we would also like to observe this signal here and see if it goes the way we expected it to go. Alright, so let's see. Let's change the data format here into binary. And so we can observe that, as we said, that our RH signal will look like this, and we expect our Q to continue being 0 until when we have the last signal turn to 1. And let's see if we have observed this. So we can see that our signal here, first of all, when you have reset equals to 0, we still have our output being equal to 0. And when our reset goes to when our reset goes to 0, then we see that we start counting, we start shifting. And we can see that our register starts shifting the way we expected it to, and Q, which is our output, remains 0 until the last the MSB of our signal becomes 1, and that's when we read 1 at our output. So it seems our circuit is working as expected, our shift register is working as expected, and so therefore I hope you've been able to learn something from this design. See you in the next video.